Okay. Yeah. So, yeah, it's really great pleasure for me to. I'm really happy to be here to give this talk. And yeah, as Yaroslav mentioned, I mean, this is a subject. This is a topic where people really have actually, which people actually have studied for more than like almost a couple of generations. And it's also very closely related to what has been discussed in this workshop. But somehow, people have not really tried to really establish the clear connection between these two topics. So I'm very happy to be given a chance to give this talk. And really, this, much of what I'm going to talk about is something I have worked out in the past and with Hendrik and Una, but I mean, it's something that due to the experiment that's going on in Seoul National University and Kyoto, I'm really picking up again with Yaroslav. So, yeah, first, as just an introduction, I want to first give you some indication about how things are, what kind of gear shift we want to make in going to superconductor. So, yeah. We are living in very strange time, we all have to admit. I mean, these kind of events seems to have occurred at least like 5 years ago when, it seems to be just, things just seems to happen on and on. But, people in this country, Brazil, probably can tell you that even, maybe the starting point should be, pushed not just a year ago, but maybe 3 years ago, because, I mean, really a totally unthinkable event has happened, Just, even no one in Korea could believe what was going on TV screens. So, I mean, but, hopefully it seems like this is proving to be much less permanent event than the two horrendous events I have shown in the last slide. And moreover, yeah, there was time before this event happened when, Brazilian soccer team really played Brazilian. Just look at this. Yeah. And we all, I think everyone in this country knows that, there was one movie which has been, really inexcusably misnamed. Come on. I mean, I have nothing against David Beckham, but give me a break. But, coming back to that kick, it's very well aligned. That Roberto Carlos kick, it is called UFO kick in Korea, but anyway, that's pretty well aligned with what has been discussed so far in this workshop. You see, the whole point why his kick made such a crazy trajectory was because of the spin he put on as he kicked the ball. I mean, clearly the ball would have curved the other way around if he made a spin the other way around. So, in fact, it really fits very well with the, spin Hall effect, if you think about it. So, in many ways, it seems to be, the whole thing seems to be fitting very well together because, like, whenever in discussing spin Hall physics, as Shuichi Murakami can tell us really well, I mean, the whole emphasis is that this is a phenomenon which can occur at very high temperature. I mean, his aim was to really show that how this can occur at room temperature even. And moreover, this is basically single electron phenomena. Let's put it this way. Even Roberto Carlos cannot kick two balls simultaneously and make it bend like this. On the other hand, people have, for a very long time, have known a system where you can actually have a spin current, which simply cannot be just described by a single particle picture. And that involved a helium-3 superfluid. I'm really not going to go into detail about this experiment on generating spin supercurrent there. I mean, it's very cool. It's potentially very cool for the kind of purpose we have in our mind, because they're generating spin supercurrent with. I mean, this is basically the same concept that Yaroslav has been talking about, generating nearly like dissipationless spin current. But then we all know that, you know, to achieve superfluidity in helium-3, which is after all a fermion, what we really need is Cooper pairing. So this is a spin current that's really carried by Cooper pairs, and moreover, you know, it's clear. I mean, this is something that can happen only below the condensation of the Cooper pairs in helium-3, which turns out to be happen at very, very low temperature, like sub-millikelvin range. So, you know, on one hand, what I'm going to talk about today is, you know, had a lot to do with the physics I mean, it's very closely related to physics we have been discussing so far, but we are still putting in important twist here that I'm going to be talking about spin current carried not by single electrons, but rather by Cooper pairs. And that's the first thing, yeah, so it would actually not happen for just any kind of system with Cooper pairing. And I'm going to show you that why it would really take spin-triplet superconductor to have this kind of physics. And in fact, you can even go the other way around and say that being able to support spin supercurrent is like one important signature, in fact, of the spin-triplet superconductivity. And I'll also show you two different instances, half quantum vortices and junction with ferromagnetic metal, where we can generate this spin supercurrent. So let's first talk about strontium luthenate and the spin-triplet superconductivity. So, you know, strontium luthenate, when you think about its normal state, I think the special point here really is that, you know, somehow it's like for having the structure it had, somehow at normal state nothing really special happens. I mean, structure-wise, it's totally identical to cuprate. And in fact, that seems to have been the main motivation for people like Yoshi Maeno to actually study this material. They were hoping actually this is another high TC superconductor material. However, disappointingly, it turned out that TC is very low, just 1.5 Kelvin. And, you know, above that temperature, it seems like it's behaving pretty much like a usual, you know, run-of-the-mill Fermi liquid. However, once they, yeah, and that's important point. So, you know, strontium luthenate series, I mean, like, nobody really understands what's the exact relationship here, but you can see here that for this oxygen surrounding ruthenium atom, the apical oxygens are not shared between different ruthenium atoms, and for this strontium luthenate 214. And in this case, we have seen very little tendency toward any kind of magnetism in the normal state. On the other hand, once you start to have like multi-layer strontium luthenate, which means that at least some of these apical oxygens are starting to get shared, then for bilayer you start to have metamagnetism, and by the time you reach trilayer, you do start to have ferromagnetism. And so in the perovskite material, strontium luthenate 113 that I'm going to mention toward the later part of the talk, where all the apical oxygens are shared by ruthenium atoms, it's a very well-known ferromagnetic metal. I mean, the exact reason why it's behaving like this is not really well understood, but, you know, it seems like it's very closely related to ferromagnetic material, but just on this strontium luthenate itself, you know, it's not really, it doesn't seem to have very strong ferromagnetic fluctuation, in fact. So, but somehow, Yoshimino somehow had all the patience to really make a high quality sample and lower the temperature all the way down to 1.5 Kelvin. And once he started to study the superconducting property, it turned out to be very unconventional. First thing is the night shift. So for the Zeeman field applied along this in-plane direction, this is a kind of like a layered structure. So this c-axis direction is very well differentiated by this from this AB plane direction. Well, once you start to apply this in-plane magnetic field, it turned out that there was no change whatsoever in spin susceptibility across the superconducting transition. And this is emphatically not something you would expect from the usual spin singlet superconductor, because spin singlet superconductor, it's like spin singlet pairing practically erases spin off the electrons when they form a pair. So you certainly would not expect something like this to happen. And also, you have a superconductivity that breaks time versus symmetry. For instance, in this curve rotation experiment, non-zero curve rotation, which is like the signature of time versus symmetry breaking, has onset exactly at superconducting transition temperature. So this is a very unusual superconductor, and it's this spin-triplet pairing part which I'm going to concentrate on. And as I emphasize, basically it means that Cooper pairing is not erasing the spin of the electrons. In fact, it doesn't seem to do anything. And the only way you can actually have this happen is if you have equal spin pairing along the direction of the Zeeman field. That's the only case where you can actually have this kind of unchanging spin susceptibility across the superconducting transition. So yeah, this is almost like, this is actually going a little bit beyond just showing that this has spin triplet pairing. It's like saying that it has it's a spin triplet pairing with equal spin pairing along the in-plane direction. Equal spin pairing when you set the spin quantization axis to be along the in-plane direction. But, we would want to have some more corroborating evidence here, because when we are saying this is a spin triplet pairing, we are actually saying something, we are actually making some statement about what kind of symmetry breaking it takes to achieve this kind of this kind of superconductivity. I mean, it's like we are breaking, as I'm going to show you in next few slides, we need to spontaneously break some kind of like a spin rotational symmetry if we want to have any kind of spin triplet pairing, which is to say, there should be some signature of this kind of symmetry breaking, and that actually has been detected almost from the onset for spin helium-3 superfluid, and that's why people immediately accepted that they have spin triplet pairing for these helium-3 atoms. So in that sense, and the key point I want to tell you today is that for the reason that very closely follows what Yaroslav has told us, actually this supporting this kind of spin supercurrent would be very strong signature of the spin triplet pairing, and very strong corroborating evidence for the spin triplet Cooper pairing in this strontium-luteinate superconductor. So yeah, let's think about what the order parameter symmetry for this spin triplet superconductor. So in spin singlet case, we just have electron pairs are in S=0 state, and that's it. There's nothing else, nothing more to talk about. However, in general, for the case of spin triplet pairing, really we need to think about the pairing at a we need to think about the Cooper pair spin state in terms of this kind of tensor. And it turns out that for the spin-triplet pairing case, it's very well parameterized by this three-component vector D vector. And the physical meaning of this D vector is that along the direction of this D vector, in the direction perpendicular to this D vector, you have equal spin pairing. For instance, if you set this Z component of D vector to be 0, then you have like spin up and spin down pair with the spin quantization axis along the Z axis. So if you assume that there's no spin polarization of the condensate, it's you end up having real this three-component D vector is going to be real up to a roll phase, and also it's basically like along this D vector direction, the spin is like Cooper pair spin comes out to be like 0. So this D vector kind of defines a symmetry direction for this spin triplet pairing. So in that sense, whereas the spin triplet Cooper pair, the full spin rotational symmetry there was originally SO3. It's kind of like by picking a single D vector direction, you actually reduce the spin rotational symmetry down to SO2. So there's kind of like a spontaneous S2 symmetry breaking that's required if you want to have spin triplet Cooper pairing. And I will show you how this can actually very simply lead to spin supercurrent. The simplest way to think about it is to just say that, our D vector just lies in a plane. In that case, the direction of the D vector can be just parameterized by this single angle, alpha. And in that case, what you can notice here is that, the direction of this D vector kind of like defines the relative phase between spin up pair and spin down pair. So if you have a gradient of this relative phase, it's like we are having counterflowing supercurrent between spin up pairs and spin down pairs. So if you have any gradient of this relative phase, it's like you're going to have spin up pairs and spin down pairs flowing in opposite directions. So it's not going to give rise to any net charge supercurrent, but it is going to give rise to net spin supercurrent. And this can be actually generalized even for the case where, this D vector moves around in full sphere, and the basic, important point is here that basically this spin operator actually generates rotation of this D vector, and it's actually very identical. This kind of commutation relation is completely identical to the commutation relation between the nanoloader parameter and Heisenberg antiferromagnet and the spin operator. So in that sense, the spin supercurrent can be defined in exactly the same way. So I have so far shown you how it's possible for the spin triplet order parameter of spin triplet superconductor to support spin supercurrent. And now my remaining goal is to show you 2 experimental setups where this spin supercurrent can be generated. And the first one I'm going to discuss is this half quantum vortex. So the definition of half quantum vortex is simple enough. I mean, the conventional Abrikosov vortex is usually, it's the case where you have H over 2e flux threading through your vortex, and you have 2 pi phase winding for your order parameter. But you see, we are having like a 2-component order parameter here, basically like spin up pair and spin down pair. So if we have a topological defect where we have 2 pi phase winding around up pairs and 0 phase winding around down pairs, then it's going to actually trap only flux not of h over 2e, but h over 4e. And another way of writing down this situation is to just say that it has pi winding in overall phase and pi winding in relative phase. So, you know, it has been shown in 70s and 80s that how this can arise in spin-triplet superconductor and superfluid. And it has attracted a lot of attention, particularly for this chiral P wave case, because, you know, the conventional if you talk about spinful P plus IP superconductor, then it's like you have conventional vortices is going to support Majorana zero mode coming from spin up pairs and another Majorana zero mode coming from spin down pairs. So in that sense, conventional vortex is not going to give you a single Majorana zero mode at the vortex core. It will really take half quantum vortex if you truly want to have single Majorana zero mode in spinful P plus IP superconductor. So in that, because of that, this half quantum vortex has attracted lots of attention. But for today's talk, I'm not really going to go into any kind of Majorana aspect of it. The question I'm really going to ask here is that since my stated purpose is trying to talk about how we can generate spin supercurrent, my point is to just think about in what case would it be energetically favorable to have half quantum vortex in your system. And it turns out to be more complicated than one might expect, because, you know, if you think about it, charged supercurrent is coupled to electromagnetic field. However, spin supercurrent, it has no net mass flow, so that also means that it's not going to couple to electromagnetic field at all. So what that means is that whereas the charged supercurrent is screened, spin supercurrent is not screened. It's not going to be screened. So if you want to talk about a single half quantum vortex in your system, it's simply never going to really work, because there's going to be log divergence in the energy. So even if one may simplistically think that, you know, since you have reduced vorticity in the charge sector, and that might, although that may sound like it's going to conserve energy, what really happens is that actually the spin sector is going to actually cost divergent energy and really spoil the whole thing if you want to think about just single half quantum vortex. On the other hand, yeah, exactly. That's one way out. Yeah. So basically, that's a very nice, good point, and I think the main point here is that basically you want to actually suppress. If we ever want to have half quantum vortex in spin-triplet superconductor, we want to start out by suppressing, looking at the system where the effect of screening would be, Meissner screening would be suppressed. Yeah. And we might also argue that, you know, our starting point has been wrong to start with, because, I mean, single full quantum vortex and single half quantum vortex, they don't even have the same topological number. So maybe the way to go is to compare single full quantum vortex with pair of half quantum vortices topological number of which would add up to exactly the topological number of full quantum vortex. So by that I mean that the case where the relative phase winding would be O plus pi for the both half quantum vortices, but the relative phase winding would cancel each other out. And here we still have some limitation because basically the repulsion coming from the charge sector will be screened, whereas the attraction coming from the spin sector will be unscreened. So in that sense, we will still have some bound pair of half quantum vortex pair. However, we can also argue that once the spin stiffness is much smaller than the stiffness for the charged supercurrent, then we are going to have finite equilibrium size for this half quantum vortex pair. And that kind of suggests to us that if we somehow are in the system whose length scale is smaller than this size of this equilibrium size of this half quantum vortex pair, maybe there we may actually be able to stabilize half quantum vortex. And that would be one way. I mean, the other way would be making a very, very thin sample, as Yaroslav suggested, but that would be one way of actually reducing the stop worrying about the Meissner screening effect. So the system we thought about is this mesoscopic ring of strontium luteinate. So here we would be, strictly speaking, we would be talking about not half quantum fluxoid rather than half quantum vortex. But anyway, what we thought about is trying to think about the Gibbs free energy for given applied magnetic flux through the ring. And what we find is that if this spin supercurrent stiffness is small enough compared to the charged supercurrent stiffness, it is possible that for the flux of H over 4E, this half quantum fluxoid state would actually have lower energy, give us the lower energy. So this whole Gibbs free energy may sound rather abstract, but then we learned in our undergraduate thermodynamics class that if we take derivative of this Gibbs free energy with respect to the applied flux, we are going to get a very measurable quantity, this magnetization, the ring magnetization. So what this Gibbs free energy graph is plotting is telling us is that whereas if we have a system where the fluxoid entry are just all full quantum, we are going to have kind of like a sawtooth pattern with the tooth of all of equal size. For this kind of ring that supports half quantum fluxoid, we are going to actually have a double sawtooth magnetization curve. And that was what was measured in this experiment published in Science by Junho Zhang and Rafi Budakian. Basically, their evidence for half quantum fluxoid consisted of this double sawtooth curve they have detected for the mesoscopic strontium luteinate ring. I mean, they really. I mean, from what I heard from them, they just grounded their strontium luteinate sample and got one piece of this side, and they managed to drill a circular ring hole through this sample, and they had a very high precision measurement device for the magnetization using this torque magnetometry. And yes. Yeah, it refers to changing of the winding number. Yeah, for the yes. So there are certainly they certainly ramped up their magnetic field very very slowly. Yeah. So yeah. So dynamics they have not measured, and they have taken lots of care over measure looking at the hysteresis. Uh, but yeah, they have some hysteritic behavior. But more other than that, I'm not really sure what kind of dynamics they observed. So and actually, one reason why they were more able to determine that they have seen this double sawtooth pattern is that they actually applied not magnetic Zeeman field not just along this axial direction, but they also applied magnetic field in the direction that's perpendicular to this actual direction. So they actually also needed in plane magnetic field to achieve this kind of double sawtooth pattern. And that seems to suggest that although people have believed that this d vector of the strontium-luteinate 214 is locked along the z-axis direction, it looks like this locking energy scale is very, very small. And for this particular experiment, actually, the d vector winding was just going out of the plane. And one way to justify it is that actually, if you have this kind of in-plane field and there is a slight polarization between spin up pair and spin down pair, with this quantization axis being defined by the in-plane Zeeman field direction, then it becomes slightly easier to introduce relative phase winding for the component with a smaller density, actually. So that may actually have helped triggering this double sawtooth pattern. So, yeah, that's kind of suggesting how this kind of Zeeman field and coupling to ferromagnet may be actually very useful in generating spin supercurrent in strontium-luteinate 214. And it just turned out that there exists a ferromagnetic material that turns out to have really nice proximity effect to strontium-luteinate 214. And that's because it has very similar lattice structure, the strontium-luteinate 113. So you have this whole series of Robertson-Popper series. And basically how you go from these monolayer to this multi-layer is that, for this single layer, none of the apical oxygen is shared by more than one ruthenium atoms. But as you go to multiple layer strontium-luteinate, you see more and more apical oxygen being shared between different ruthenium atoms until 114, 113, all the apical oxygens are actually shared between two different ruthenium atoms. And basically, it's made out of the same material. It's like if you just look at the ruthenate plane, it all looks more or less same. And there is a bit of a lattice mismatch. But if you're thinking about a situation like trying to fabricate thin 113 film on top of 2-on-4, basically the 1-on-3 film can just follow can be well strained to just follow the lattice constant of the 2-on-4. And the other aspect of this 1-on-3 ferromagnet is that it's metallic and it has very high Curie temperature. The Curie temperature is like 2 orders of magnitude higher than the superconducting TC of 2-on-4. So basically, you can just consider the Curie temperature to be ferromagnetism of this 1-on-3 to be just a given property that's not really affected in any way by the 2-on-4 superconductivity. And it's also, this is actually a very nice instance of, people have published tons of paper on this ferromagnet superconductor junction, but this particular instance is, I would claim, is especially interesting because most of the cases people have actually talked about junction between spin singlet superconductor and ferromagnet, and it's like spin singlet superconductivity is just, it doesn't agree very well with the ferromagnet because opposite spin pairing just doesn't agree very well with the spin imbalance, any kind of spin imbalance. So if you really want to have proximity effect in that kind of system, superconducting proximity effect in that kind of junction, you would require things like spin flip scattering and all kinds of different things that would actually depend very, very strongly on the interface impurity. On the other hand, between spin-triplet superconductor and ferromagnetic metal, the proximity effect is more or less same as any kind of proximity effect between any kind of ordinary metal and superconductor. As long as the magnetization direction of the ferromagnet is parallel to the equal spin pairing axis of the spin-triplet superconductor, it's just not very different from any ordinary metal. And which is to say, impurity scattering is not like the very intrinsic component of the proximity effect in this case. And in case of this strontium luthenate ferromagnet superconductor junction, it's all the more true because the Seoul National University team was able to obtain very, very clean interface, which looks very nice and clean even on the atomic scale. So, although the experiment has been performed on the proximity effect between this 2-on-4 and 1-on-3, and the method is pretty straightforward. Basically, they have this 2-on-4, 1-on-3, and not sure why they were not able to avoid having this gold, probably because of this contact issue. And basically, as any such junction, as would be true for any experiment on any of these kind of junction, basically they were measuring junction voltage. They were measuring for given applied current, the voltage voltage drop across this junction. And by measuring this voltage drop, as they lower the temperature, they have seen kind of like a signature of multiple transition by looking at this derivative of resistivity with respect to temperature. And they have taken that as evidence for like the multiple superconducting transition, which is to say the highest temperature is like the superconducting transition for 2-on-4, followed by this lower temperature transition showing kind of temperature scale at which this proximity-induced Cooper pairs start to come into existence in 1-on-3 and gold. And moreover, yeah, using this, by looking at this DI/dV curve, they were able to extract out the pairing gap at each interface. And through that, they managed to establish that basically the proximity effect induced gap persists all the way down to the interface between 113 and gold, which is to say that, we have long-range superconducting proximity effect between 214 and 113. And another signature thing they have noticed is that 113 being ferromagnet in this setup, it's very natural that when they do magnetic field sweep, there's like a jump in resistivity associated with the movement in the domain wall. But somehow those movements on the domain wall had no effect on the induced pairing gap. So apparently this proximity effect is completely intrinsic with very little effect coming in from impurity scattering. And so in that case, I think it's reasonable to say that this Andreev conductance for spin up pairs and Andreev conductance for spin down pairs can be treated pretty much independently. So this is kind of like the starting point we are thinking about for generating the. So this experimental result is providing the kind of the starting point for how we may generate spin supercurrent in this kind of junction. Yes. Well, this is not impurity in this P-wave superconductor, but rather impurity on this 113. Well, I mean, this is, well, domain wall is about, it's domain wall, I mean, it's although the different domains have different magnetization, if these magnetizations are all parallel to the equal spin pairing axis, then I think we can reasonably claim that it's not really going to have big effects on the proximity effect. So kind of junction structure that we are starting to think about right now is basically having two well-separated 113 lead on top of 214 bulk. It's also experimentally easiest kind of heterostructure to fabricate. And our point of view is that in that way, we can think about the Andreev conductance for spin up and spin down separately. But you see, what's going to be important in thinking about how, say, the boundary condition between these the current at two interface, the left interface and right interface, is that spin current, charged supercurrent, is going to be absolutely conserved. On the other hand, when the spin up pairs and spin down pairs, this is in this kind of Andreev conductance, Andreev reflection with bias, non-zero bias voltage, we are certainly going to have winding of the phase winding. And it turns out that because we are thinking about the spin up pairs and spin down pairs separately, certainly it's possible that the spin up pairs and spin down pairs are going to have phase winding at different rate. But on the other hand, that's completely equivalent to saying that the D vector of the 214 spin triplet superconductor is now going to persist. But then as Yaroslav mentioned in his talk, if you have this kind of precession of the spin order parameter, that's actually going to give rise to Gilbert damping in this kind of solar state system. So we have different boundary conditions, two different boundary conditions. One for the charge conservation of the charge supercurrent, and the other is for the Gilbert damping of this spin supercurrent. And depending on whether we have alignment or anti-alignment of this magnetic lead, we are going to have different current flowing through this junction, and that's going to actually give us the magnetoresistance as evidence of this spin supercurrent with this d vector precession. So with that, I would like to conclude my talk. So the biggest point I want to make here is that spin supercurrent should be really considered a generic feature of spin-triplet superconductor, and two possible experimental signature. One experimental signature that has already been seen is the half quantum vortex, and the other that we want to actually figure out now is the spin supercurrent generated in the ferromagnet spin-triplet superconductor junction. Thank you all for your attention.